So you have added, subtracted, multiplied, and divided rational functions, and today you're going to learn how to graph them. So I want you to be able to graph rational functions and to transform them. Now, a rational function is a function whose rule can be written as a ratio. Again, you'll see the word ratio in the word there, of two polynomials. Its parent function is written as f of x equals 1 over x, so no transformations there, and it is a hyperbola. Now, a hyperbola has two separate branches. Just like logarithms, hyperbolas may have asymptotes. Now, asymptotes of the parent function of a hyperbola are going to be x equals 0 and y equals 0. So remember, x equals 0 is a vertical line. Y equals 0 crosses the y-axis, so it's a horizontal line. All right, this is the first rational function we're going to look at, and you can tell how the graph changes by looking at the location of where the numbers are. So think back to this. This is the parent function. So when we have a change here, it follows just what you've learned before. If it affects the x, it's left or right. If it's not with the x, then it affects the y, or vertical. So let's look at the graph over here. This is a graph of a hyperbola without any transformations. So this is f of x equals 1 over x. Okay, rational functions can be transformed by using similar methods to those you use to transform other types of functions. Adding and subtracting transforms functions by sliding them up, down, or left or right. Multiplying transforms functions by stretching or compressing them. If we want to transform rational functions, we use this graph, the parent function, and then we describe the transformations. So you just basically look where the transformation takes place. Here our transformation is taking place with the x, and it's the same thing as we did before. You think about this kind of as setting it equal to 0. So x is going to equal -2. Well, if we start at 0, 0, and we end up at -2, our function has moved 2 units horizontally to the left. Now here we have two transformations happening. We have, this is showing us that we're going to move 2 units. If we set it equal to 0, x is going to end up at +2, starting at the origin, ending up at +2. So we're going to have as a horizontal translation to the right 2 units. Now this is where the vertical translation takes place. So if it's not with the x, it's not horizontal, it's going to be vertical. So this transformation would be from the parent function, 1 over x, is going to move it horizontally 2 units to the right, vertically 3 units down. Okay, now for a rational function in this form, the graph is a hyperbola. There's a vertical asymptote at the line, or vertical asymptote at the line x equals h, and the domain, x can be everything, but it can't be whatever h is, because that will make your denominator equal to 0. So you see here, this is going to go forever in this direction to the left, forever in this direction to the right, but there's nothing right here, and that's where your vertical asymptote is. So the domain and the range are pretty easy. They're all the numbers except for the asymptote. All right, so let's look at the properties of hyperbola, zeros, and vertical asymptotes. We're given this function right here. Let me slide this up a little bit. And we want to figure out what the asymptotes are and what the domain and the range are. So the asymptotes are the value right here is going to make the denominator undefined. So you're going to have one at x equals -3. You're going to have another one right here at y equals -2. So that would be, oh, let me slide the graph down. Here for the parent function, the vertical asymptote is at x equals 0, because this would be set equal to 0. And there's nothing out here for y, so it would be like +0. So they really don't show you here on the graph, but we'll just write that in here. This is y equals 0. This is x equals 0. Okay, so going down here now to our function, we can see that x is negative, x cannot equal negative 3, so that's going to be the asymptote where the graph is not going to cross, so x equals negative 3, and here's our y equals negative 2. So that sets the graph up. And then our domain, we can't have a value for x that is negative 3. So the domain is the set of all numbers x such that x is not equal to negative 3. And we do the same thing with the range. The set of all values x, numbers x, such that, oops, that should be a y. Let's change that to a y. Range is y. So we'll make that a y, such that y is not equal to negative 2. All right, now I just want to, before we go on, I want to talk about a discontinuous function and continuous function. Discontinuous functions are functions whose graphs have one or more breaks or gaps. So this would be discontinuous because it's breaking right here. It's not connected, so they have disconnected parts to the graph. A continuous function is a function whose graph has no gaps or breaks. So a continuous function is going to look, that could be one example. You've graphed a lot of different continuous functions. You've had linear, quadratic, exponential, logarithmic. So rational functions, we're going to graph some rational functions that are discontinuous, again, which means they have breaks and gaps due to the asymptotes. All right, on the next page, not all graphs of rational functions are hyperbolas. Okay, so let's look at a graph to get some more information about it. If it's not in the form that it was on the first page, then you'll want to factor the numerator and denominator to get the information out that you need. So setting the factors in the numerator of the rational function equal to 0 will give you the x-intercepts. So let's do that over here. We're going to, and the x-intercepts, remember, are right on the x-axis. When y equals 0, you have your x-intercepts. So if we set this equal to 0, then we know that one point on the graph is going to be at x equals 3. Another point is going to be at x equals negative 2. So these help you find the x-intercepts. Now, the vertical asymptotes you'll find in the denominator. So this would be your asymptotes. And it's going to set this equal to 0. It's going to equal negative 1. All right, so when we set the factors in the denominator, the rational function equal to 0, it will give you the vertical asymptotes. And vertical goes up and down. Okay, so that's how you find them from this function. Now, I want to show you a graph of a rational function. This one has zeros at 3, 0 and also at negative 1, 0. So that means if we were to write the function, in the numerator we would say x plus 1, also x minus 3, and since our asymptote here is at x equals 2, in the denominator, we would write x minus 2. So I want you to be able to go back and forth from the function to the intercepts and the asymptote, and from the graph back to the function. All right, let's talk about some horizontal asymptotes. Some rational functions will have horizontal asymptotes. Now, not all of them will. And sometimes the graph of a rational function will cross the horizontal asymptote. However, the graph of a function will not cross the vertical asymptote. Now let's think about why that is. The reason it will not cross a vertical asymptote is because you look at the factors in the denominator of a rational function to find those vertical asymptotes. If the value of x causes the factors to equal 0, the function's undefined for that value of x. All right, so let's look and see how we figure out what the horizontal ones are. This is how we get the denominator to find the vertical ones. So you always look at different pieces of a function to find different pieces of information. All right, now, there are three different things that can happen with horizontal. You may have no horizontal asymptote. You may have one that is the line y equals 0. And you may have one that is the leading coefficient of P over the leading, whoops, I almost crossed that off there, over leading coefficient of Q. All right, so I'm going to give you an example of each one. Basically what this says, if you look at your rational function, so I'm just giving you one here that is x squared plus 2x plus 1 over x minus 1. This is P, this is Q. We're going to look at the degree. Here the degree is 2, here the degree is 1. So that means the degree of P, what's in the numerator, is higher than the degree that's in the denominator. So that means there is no horizontal asymptote. Now, if the degree of P is less than the degree of Q, I'm going to give you an example of that one. So here, the degree in this one is 1. Degree on this one is 2. That means our line is y equals 0 for our asymptote. All right, if the degree of P equals the degree of Q, and here's the example for that, they're both squared. Now, they could be both cubed, they're both to the fourth, it doesn't really matter. But if they're identical, then what you do is you take the leading coefficient of P and the leading coefficient of Q. So make sure you're in standard form. That means our horizontal asymptote is going to be 3 over 2. Okay, and just a reminder, the leading coefficient of a polynomial is the coefficient of the first term when the polynomial is written in standard form. Okay, a couple of things here. We're going to identify the zeros and the asymptotes of each function. Again, remember to factor each function first. So I'm factoring them for you here. Okay, so the zeros, these will give us the zeros. This gives us the vertical asymptote. And the degree, let's see, the degree will tell us the horizontal asymptote. Okay, so setting these equal to 0, I know that I have zeros, so this is where a point on that function is on the x-axis. It's going to be at 4 and negative 1. Here, I have none for the horizontal asymptote. Now let me show you why. The degree on the numerator is 2, degree on the denominator is 1, so that means P is the numerator, Q is the denominator, so P is greater than Q, so that means there are no horizontal asymptotes. All right, now we'll go down to the vertical asymptotes, which we find in the denominator, and we set that equal to 0, so x is 0. Next one. Factoring the denominator is the only one that we needed to factor here. Our 0 come from the numerator. Vertical asymptotes are here. So we set this equal to 0, and this is going to have a point at x equals 2 on the x-axis. Horizontal, we have to look at the degree. The degree here is 1. Degree here is 2. So that means P is less than Q. So P is less than Q, which means our horizontal asymptote is y equals 0. And then we set the denominator equal to 0 because that's where we find our vertical asymptotes. So vertical asymptotes are at x equals 1 and x equals negative 1. Last one. Here we're going to factor out a 4, and we're left with x minus 3 over x minus 1. So our zeros here are going to be, you just take wherever there's an x, set it equal to 0. So x is going to equal 3. Horizontal asymptotes. Well, let's go to our degree. Here the degree is 1. Here the degree is 1. So that means they're equal. So now we go to the leading coefficient. Well, lead coefficient here is 4. Lead coefficient here is 1. So we'll just put 4 over 1. or that will be 4. That's where we're going to have a horizontal asymptote. Vertical asymptote, we just take the denominator, set it equal to 0, and we have x equals 1. All right, we'll do the holes in the graph the next day.